So we've spent quite a bit of time now talking about probability and inference, but how do we incorporate these into making decisions? So let me make this concrete with the following example, where I have 3 lotteries and I want to decide which of these lotteries should I play. In the first lottery, if I play it, the first thing I do is I pay $1, and then I get a 1 in 1 million chance of winning $1,000. In the second lottery, if I play it, I first pay $1, and then I get a 1 in 1 million chance of winning $1 million. And in the third lottery, I first pay $1, and then I get a 1 in 10 chance of winning a measly $10. So intuitively, if you look at lotteries 1 and 2, we pay the same amount, and then we have the same chance of winning, but in the second lottery, we stand a chance of winning way more money than the first. So intuitively, we shouldn't even consider playing lottery 1. Between 2 and 3, here it's less clear, because a 1 in 1 million chance of winning is really low. A 1 in 10 chance is much, much higher, but the amount you can win is much smaller. So how do we decide between which of these to play? In general, there isn't a unique solution to this problem, but what we can do to quantitatively and rigorously reason about such decision-making problems is to, for each scenario that we're deciding between, compute some kind of cost or some kind of reward. So for example, we can look at some sort of average amount we would win if we played each of these lotteries. So if we play the first lottery, the first thing that happens is we lose $1, and then we stand a chance of winning $1,000. But it isn't guaranteed, right? So we're not just going to magically walk away with $999 for sure. So what we could do is we can weight this 1,000 by this chance. Okay, so this 1 over 1 million. You can think of this as downweighting this unlikely scenario that we get $1,000. And if you compute this, you'll see that this is equal to negative 0.999. Okay, so we probably don't want to play this lottery. The average in this way that we just made up some way to compute an average is negative, so that doesn't look very attractive. What about the second lottery? Well, using this way that we just computed this average above, we would get, first we lose $1, and then we stand a chance of winning $1 million with probability 1 over 1 million. And this thing is going to be minus 1 plus 1, which is equal to 0. According to this kind of average calculation for amount of winnings, accounting for the cost, of course, of paying $1, this seems like perhaps it's not so bad. The average amount, that is 1, is 0. But somehow it seems like the chance of winning is actually really, really low, 1 in a million. We're very likely to just lose that dollar and that's it. Alright, so what about this third lottery? Here we would lose $1, and then we stand a chance of winning $10 with probability 1 over 10. And if we do this, then again we have minus 1 plus 1, which is 0. Okay, so these two have this same average amount 1 using this way that we just made up for computing these average amounts. Perhaps what we want to do is look at some other things, such as how likely is it that we actually win. So here it's really unlikely that we'll win, and here it's more likely. So perhaps between these two, maybe it makes sense to try to go for this $10. Okay, so this gives a flavor of what we mean when we talk about decision making. To reason about these kind of decision problems, a key tool we'll be using is what's called the expected value of a random variable. And you can think of this as, in making decisions under uncertainty, often it makes sense to think about some average scenario that we should expect. And expectation is all about taking an average, accounting for how likely different outcomes are. So in 608.1x, we talk about expectation here, and then we're going to be seeing it again when we reach the third part of the course, when we talk about learning probabilistic models. And the idea there is that what probabilistic model makes sense for your data can be thought of as decision making. We're deciding which model to use instead of, for example, deciding which lottery to play.